Hey guys, Coach Nate here. Welcome back to another video. Thank you guys for selecting me to watch and to learn. So real quick, this is me. I am Coach Nate. This is my Instagram. You can go ahead and follow me here. It's the_Nate_Dawg, spelled D-A-W-G. And today marks, it's May the 4th be with you. Today marks, I believe, 1 or 2 years, I can't even remember now, since I've taken the MCAT, or Medical College Admissions Test. That 8-hour exam that tests you on physics, chemistry, biology, biochemistry, reading comprehension, and psychology and sociology all in one, and it's like a giant thing. But anyways, I'm a little bit rusty today, but I'm going to try to explain just a little bit of how I view the world in terms of like the flow of knowledge and how I look at science, like from my perspective. So let's go ahead. I got my little pad out here. I've got to kind of log back in here. This is kind of an impromptu video, so please excuse me if I'm a little like jump around-ish because there's not really a lesson plan. I'm just kind of doing this off the dome. So on my little pad here, I kind of have mapped out how I view science. And I see science as this sort of kaleidoscope where you can zoom in and out. Like it's like a microscope as well. Like you zoom in and then you get deeper into a subject and you get closer and closer to like pure math. And then you zoom out and you keep on zooming out until you get past organisms, and then you get past like the planet itself, and then you get solar systems and galaxies. And the universe and all of that stuff until you get to where we can't even comprehend. And that's where sort of like theology comes in and just speculative, like theoretical physics, basically. But let's go ahead and kind of run through this a little bit. I'll kind of get this little red guy. So if I were to start, I think I would start at math is where I would start. Like, honestly, everything starts at again, like we kind of just, in my opinion, like this can offend some people, I'm sorry. I feel like when humans don't know something, we kind of just throw God at it and we're just like, yeah, that's God, because we don't know how to calculate that. And, that's just kind of my opinion, so apologies if that upsets somebody. But so anyways, we kind of start at the unknown or theology or, kind of spiritual stuff, right? Then you get into math, and we know like math is the basic fundamental thing that makes up kind of everything else. It's this how we can calculate things. So then you go from math down over to physics. Then you zoom out of physics. What do you get? You get physics at a bigger level. That's chemistry. You zoom out of chemistry. What do you get there? Well, then you get chemistry at a more organized level, like organic chemistry or biochemistry or physical chemistry, which we won't really get into as much, or inorganic. And then after you zoom out of biochemistry, what do you get? You get biological systems. That's like biology. That is cells. That's cellular and molecular biology. That's, like the Golgi apparatus, all that stuff. Then you zoom out of that, and then you get systems working. So you get like anatomy and physiology. You get ecology after that. You get behavior, human behavior, stuff like that. Once you kind of go out of there, then you kind of get, that's where the psych-soc kind of branches off a little bit as well. So you've got psychology, sociology, that kind of branches out. And then the social sciences are all kind of like right here, I would say. And they're kind of out off of ecology. So ecology is like all populations of animals. And then you have kind of like sociology and human psychology, which are like not necessarily smaller or less important, definitely not less important, but like a branch sort of in that realm of the zoom, if you will. So like zooming in and out in science. So then after you've got that, then you kind of get into like bigger things like the climate, like climate science. You get microclimates, and then you get global climate. Then after you zoom out from earth science, then you've got astronomy, and that's kind of where you're looking at, okay, now we're looking at the planet. We just zoomed out so much that we're literally looking at the planet now. And then after you zoom out from that, then you're going to get into like galaxies and the universe. And then once you can't zoom out anymore, then you kind of get into theoretical physics and theology. And then the reason I have this kind of line back here from theoretical physics is because of that just builds back again into physics and then more math, right? And this kind of goes back as well. Physics and math kind of build off each other. And then there's pure math, which is just like straight up math for math's sake, which is pretty cool. And a lot of people, well, I shouldn't say a lot of people. There's a niche group of people that really enjoy pure math. So we probably won't talk too much about it on this channel, but just know that that is there. Now, how does this kind of build into what this channel is about? So you know that this is a fitness channel and a science education channel and also a gaming channel. Let's focus on the fitness and coaching aspect. So what do I do for a living? I'm a coach. I'm a personal trainer at Blinnergy in Woodinville, and I work for Exos at Google as well currently. And that's kind of what I do is I work with people focusing on like body recomp and strength specifically. So how we develop strength and how we develop and becoming an athlete, right? So how does this all kind of relate to that, and why does it matter? Well, if you zoom, this is another zoom again, right? So we can zoom in and out. And if we start here at performance, that's kind of looking at you playing the sport. Like I was a lacrosse player. Let's say we're playing lacrosse and we got to have certain skills and stuff, right? So what are skills? They're motor skills. And where does that kind of come in? Well, that kind of adds all of these things together in a loop, and they're all working together, zooming in and out on this, by producing movement. Where does movement come from? Well, oh my gosh, this goes back to the math and the physics and all that stuff. So we've got math up here again. Apologies for my horrible writing, which is going to feed into physics. And then what is physics? Well, okay, it's all of these equations and stuff, and it kind of explains like how the world works as we know it. Well, why does that stuff? Why does that matter when it comes to performance and being an athlete and being a human being? Well, let me tell you. So, what are we made of? Right? And we're made of cells. Human beings are made of systems, which are made of organs, which are made of tissues, which are made of cells. See, this is going back down. We're zooming in right now. Then those cells, those are made of macromolecules like proteins, like actin and myosin, which we will talk about. And then those macromolecules, those are made of smaller molecules. So, for instance, like functional groups, right? And then those functional groups on molecules, like what are those made of, and why do they have properties, and why do they interact in the way that they do? Well, that's because they're made of atoms, which are elements, which have certain properties, and they all interact differently because they have, let's say, like carbon, for example, right? Like it's got 4 valence electrons. That's the reason why it's so important in the body, because it can make 4 connections. And this one atom, this one element kind of defines like carbon-based life forms, right? Like we're carbon-based life forms. This one atom and some more, which we'll talk about pretty soon here, kind of dictate how our biological systems run. So like, how do we get performance? Well, it all starts with just math. Like we're just math in space, and we got here somehow. Okay. So anyways, that's kind of how I view science, and like the flow of knowledge is it's just like a zoom, like you're zooming in and out and asking different level questions. So like there's a math level question, and then there's a performance level question. Which would be like, okay, well, how do I perform the clean and jerk? So, you got to you're looking at the person now from like a third person's standpoint. And you're like, okay, well, here's your grip width. And that's a power exercise, focusing on how fast you can move something in as little time as possible. Which is really funny. Olympic weightlifting should honestly be called powerlifting, because there's way more power involved in that than there is in powerlifting, which is purely a strength sport. And it's not about how fast you can move it. It's just about how efficiently you can move something, and then using that efficiency to move as much weight as possible, no matter how long it takes. So honestly, they should really switch the names of those two sports, but I won't get too much into a rant there. Let's go ahead and zoom out here for a second. So first we have math. Okay, so let's kind of break down all of these things a little bit at a really like high basic level. So math fundamentally, when I think about it and when I use it, I think about functions. That's what I think about. I think about like input and output and like quantifying things. Like there's numbers, there's number lines, you can get into the whole world of numbers, and mathematicians will tell you a lot of things about that. For now, we'll talk about like basic things, like if you remember y equals mx plus b, right? Back from your school days. So like slope-intercept form. All right. So you have an input. This is a slope, which is just another modulator. You have another modulator, your y-intercept. That's like where something is. Okay, at a very basic level. And then you have, of course, you have an output. So that's just an example of a kind of function, all right, at a very high level, like a very basic level. So let's kind of break this down a little bit more. So we've got an output, okay, equals, like this is what a function is, some function of some input at some location in space. Okay, so at a very high level, that's what math is. It's an output, some kind of output because of some function that an input was put into at some location in space. That's math. All right, so like an example here, so of a function would be like slope exponent, like, you know, getting into orders of magnitude. You know, you've got other kind of additional transformations. Like math is extremely useful. Like take the Fourier transform, for example. Like that was used in World War II, I believe, to like literally win the war. You know, additional transformations and just like other information you can put in there. Okay, so again, at a very high level, that's what math is. It's just simply it's getting outputs after putting some input into a function, and it happens to be in some location in space. Sometimes it doesn't even have to be in a location in space for some things. Okay, but that's kind of how we'll look at math. Okay, so that was math. Now what is physics? All right, physics is the application of that math. And chemistry is going to be the application of physics. So what is physics? Let's take a look. I'll give you physics in 7 like fundamental units, right? So let's take a look at what physics is. Physics is the study of how things exist. Basically, it's basically how things exist. Like they just exist. Why do they exist? That's physics. All right. So real quick, we have our SI units, so our standard units. We have meters, all right? We have seconds. We have kilograms. All right, now all of these things can be slid up and down to get bigger or smaller by different orders of magnitude by applying math to them. So like a kilogram is 1,000 grams, for example. But we use the kilogram as like kind of the fundamental unit, especially when we're talking about like lifting, for example. You know, like a kilogram is like 2.24 pounds or something like that. Don't quote me on that, but it's, you know, a little over 2 pounds. Then we have temperature. But Coach Nate, why did you put a K right there? Well, that's because of in physics and in like fundamental existence, temperature is typically measured in Kelvin instead of like Celsius or Fahrenheit. So that's why we put Kelvin, okay? Then next, we have candelas, which is a measure of light intensity. I don't know very much about this. You're going to have to ask a theoretical physicist to tell you all about candelas. I don't really know much about them, other than it has to do with luminous intensity, and that is the fundamental basic unit of luminous intensity. Okay, so get back to kilograms real quick. I'm not sure I mentioned that kilograms means mass. That's like the measure of mass. We'll get to all of this after I get the next units. So then we have the ampere, okay, which is a measure of current or electrical current. It's like the flow of electricity. And that's really important when you're thinking about electrons. And then when you're applying this to chemistry or biology or biochemistry, because we send electrical impulses to move. Like I am literally, this movement right here, it only exists because I'm adding all of these variables that I'm showing you on the screen right now together into a biological system. Okay, so real quick, I really, not to say I like disagree, maybe this is ignorant, but I disagree with using amperes as the SI unit, and I'll tell you why. It's because an ampere is a coulomb per second. Okay, so like it is derivable. Like the other ones, meters are meters. Like that's it. Kilograms, that's a kilogram. Amperes is a coulomb per second. So that's why I think it's a little, kind of wobbly on the SI thing. But that's just my opinion. And then, of course, I also like to use Q for charge on this one. So it's like positively or negatively charged. That's where I think the SI unit should be. But again, that's not the convention. That's just my opinion. So we're going to go with amperes for what the actual conventional SI unit is. And then what else do we have? Next, we have the mole. Okay. So this is another important unit. This is like amount. Like this is like how many things are there. That's how you measure like how many things. Like a mole of something is how many thingies there are. Like if you look at molar mass and stuff, which we'll use a lot in chemistry. So, okay. Again, we're in physics right now. So let's go back to this a little bit. Let's kind of dive a little deeper here. So back to the meter. What is a meter? Right? Let's get a little bit different color here. Let's go with purple for now. Okay. A meter is a measure of distance, length, or displacement. So we'll talk about the difference between distance and displacement in a later video about physics. Okay, so that's what the meter is. All right, and we'll draw a little picture here. This, like, it literally describes space. Like, it describes where something is in space. Like, you can get volume out of this. All right, so we have meters. And then we have meters squared. That's area. See, so like I can draw a square right here. Okay, that's how you get area, is when you get meters squared. Then if you add another element to this, well, that's how you get a cube. Okay, so meters cubed, right? This is how you add orders of magnitude of space. So how you get from a single dimension to two-dimensional world to a three-dimensional world. If you add another one, I can't draw this because we can only think and see in 3 dimensions. We live in 3 dimensions. But if you add another one, that would be 4 dimensions. And if you go into the pure math, then you can get into like 5th dimension and all that stuff, 5D chess, whatever. All right. Let's get another color and let's talk about seconds. So that was meters, right? That is the measure of distance, length, displacement, like where you are in space. Like that is how you describe space itself. With meters. You can build a world using that, okay? Now, in this world, there's another sort of dimension on top of just, physical space, all right? And that is time. Time only moves in one direction. Space can move in the positive or negative direction. So time only moves forward, and it's in seconds. Okay. So what is time useful for? Time is all about like some variable over t, which could be seconds, hours, minutes, whatever, however you want to measure your time. And it's useful for measuring rates, right? So like how fast something happens. So like that power equation for when you're lifting a weight really fast, that's going to have to do with time, obviously, right? So this is very basic. Time is just, it's seconds, all right? It's literally just time. It is, I was in that moment, now I'm in this moment. Let's go ahead and get into the kilogram. So what is the kilogram? Okay, maybe I should write this down. I should say measures time. Time, okay. All right. Now let's get into the kilogram, okay? So the kilogram, that is a measure of mass. Okay, so like what is mass? Like that is how you take up space. Like we got space already and we got time. So now if you want to put stuff in that space and know how much space that thing sort of takes up, this is kind of hard to explain. That's mass. Like it's another fundamental unit. You can't break it down more than that. Why is mass relevant? Why do we care about that? Well, mass has to do with force. Okay, a force has to act on something with mass. If you don't have mass, you don't get force. F equals ma, right? Mass is literally in the equation. And then you can expand that into work, power, and then energy. Mass is a super important thing, right? You can use, if you have a force applied to a mass like gravity, for instance, then you can get something like weight. So when you step on the scale, that weight is your mass multiplied by gravity. Okay. Let's see here. Another thing about mass is, you can measure momentum. Momentum can't exist without mass. Therefore, impulse can't exist without mass. There's also these, derivatives called snap, crackle, and pop, believe it or not, which are just after impulse. So, and that's, we can get into that again into another video, but that is why mass is important and why we care about what that is. So this is basic level physics, right? Now let's get into temperature. I'm going to go ahead and use a blue one for this, just because we could use a little bit cooler temperatures in this heat now. Temperature, what is that? So Kelvin is a measure of temperature. I always spell temperature incorrectly. I always want to put an extra U in there where the E is, but that's okay. Let's see here. So 0 degrees Celsius, that's freezing. That's also, I believe it's 32 degrees Fahrenheit, 0 degrees Celsius. That's equal to negative 273.15 Kelvin. Okay? So anytime you have something in Celsius, if you wanted to, well, you've got to convert it from Fahrenheit to Celsius and then from Celsius into Kelvin if you want to apply these equations to something that you're studying. So, for instance, like in the human body, things are like 25 degrees Celsius or 37 degrees Celsius, for instance. So you'd have to convert that to Kelvin, so like 310 degrees Kelvin, before you can actually put it into the equation. What is temperature useful for? A lot of things. This whole space is gonna have to take up temperature. So we've got like absolute zero, right? That's like when everything stops. Okay, but let's go ahead and see what does temperature like do. Like it's part of enthalpy. That's something that we'll talk about all these things eventually. Okay, energy's got to go somewhere, and usually it's dissipated as heat. Okay, especially in the human body. Pressure. It's involved in pressure. It's involved in thermal expansion. Okay, so like that's why Architects, when they're building a bridge, they have to think about, well, is the materials that I'm using, like, what about winter versus summer? Is there room for expansion so that cracks don't happen as much, right? So thermal expansion, that's another thing that temperature is involved in. Another thing, believe it or not, is volume. Like, think about a hot air balloon, right? You turn up the heat, the pressure goes up, or the volume expands if you have an object which the volume can expand, right? So that's another thing that temperature is involved in. And again, believe it or not, this is where time, it kind of ties in with all these things. So like meters, seconds, kilograms, temperature has a relationship with all of these things. And another example is reaction rate, right? So like when we look at Michaelis-Menten kinetics later, and when we look at chemical reactions and exothermic reactions and endothermic reactions, that's going to have to do with temperature as well. Okay. All right. And then obviously, for now, we'll end on entropy. Okay. The thing that can only go up, it cannot decrease, but this has a lot to do with temperature as well. Okay. So that's why temperature is so important. All of these things are fundamental to just things existing at all. Okay. So we've got, length, displacement, distance. That's our meters. We've got our, that has to exist on a timeline. That's time in seconds. Then in order for something to actually take up space, it needs mass. And then you can apply cool effects like temperature, and that changes the states of matter, for instance. Okay. All right. And then we've got candelas. I don't even know if I'm saying that right. I'm not a theoretical physicist, and I don't work a ton with light. I used to do spectrophotometry in my chemistry lab in undergrad, and we did environmental chemistry. We were looking at, dissolved organic carbon, for example, in estuarine waters in California, to like after a fire versus before a fire and all that stuff. So we could get into that in a whole another talk, but I still have no idea what a candela really is. So I'm just going to draw the sun and be like, yeah, that's pretty intense. Okay. It's a measure of luminous intensity. So like you turn the brightness up on your phone versus turning it down. That would be candelas, I would imagine. Okay, cool. So I'm glad that's that, because of temperature took up a lot more space in our biological systems here. Okay, so now let's talk about current. So amperes, that's a measure. I'm going to change the color again. I might as well. Let's go with, no, we're going to keep yellow for this. Current, that's amperes. We're going to put that here. That is just a measure of, electrons moving through a system. All right. What's something interesting about that? Let's go ahead and erase some of this stuff about temperature so we can talk a little bit more about our ampere. All right. So in order for there to be current, you need some sort of charge. So that's Q. That's either positive or negative. All right. For example, let's say you have, an electron that's negatively charged. That's a very fundamental thing. Like electrons are negatively charged. That's Q. Protons are positively charged. That's Q. Okay. And then you can apply this to bigger things like atoms and molecules and stuff like that. Let's see here. So 1 coulomb, that's like the fundamental unit of charge. And then in 1 second. So anyways, 1 coulomb per second, also known as 1.609 times 10 to the negative 39 charges, like units of charge per second. That is 1 coulomb. Okay, that's the charge equivalent to like either positive or negative. If it's negative, that's an electron. If this is positive, that is actually a proton, also known as the nucleus of a hydrogen atom. That's a proton. Okay. So when you add a proton and an electron together, you get hydrogen. So you see how when I apply physics, I get chemistry? So chemistry is next, right? When I apply that physics, that fundamental thing that exists and describes existence, then I can get other things. So I get chemistry now. So this is a hydrogen. I'm kind of covering it up with my face here. But if this was on the periodic table, our we'll talk more about this in chemistry, but our atomic number is 1, which means it has 1 proton. And then because of now we're talking about elemental hydrogen and not just a proton, it's got an electron as well, which means that it's got I can't remember if the mass is like 1.08 or something. I think it's 1.08. And that's because there are isotopes of hydrogen that exist. So the average atomic mass unit of hydrogen, that's what that little thing is, average mass, is a little higher than 1. Because there are other isotopes of hydrogen that exist. So anyways, we won't talk too much about that right now. But that is charge. That is current. Like that's why that thing exists and what it is. So let's go ahead and erase this stuff here. So now we are left with the last fundamental thing about existence, and that is the mole. Like that is how much of a thing there is, so that you can then convert mass into moles and moles into mass again, and you can get like yields of chemical reactions, right? Later in chemistry. So the mole is simply, if you've heard of Avogadro's number, this is like, it's a measure of amount or quantity. Okay, that's what the mole is of a substance, of like of something. We'll just call it X. So that's where math is applied again, right? It's a function. Like it's some amount of something, some quantified thing. All right. Sorry, my foot has fallen asleep here. I gotta switch which foot I'm sitting on. So let's talk about the mole a little bit. Like, what is the mole? That is 6.022 times 10 to the 23. I don't even know what that number is, 10 to the 23. So if 10 to the 6 is a million, right? 10 to the 3 is 1,000, 10 to the 2 is 100, 10 to the 1 is 10, 10 to the 0 is 1, and so on and so forth. This is 10 to the 23 things. And that is like how many of those things are in a mole of that thing. So the abbreviation for mole is MOL, and the full word is E. So you saved one letter. Congratulations, science. Awesome. So 1 mole, let's go ahead and erase this. Why are moles important? Like, why do we care about that at all, right? So we already said is useful in calculating yields of stuff in a chemical reaction. Okay, so we got that. Is useful when you're talking about specific elements on the periodic table. So the mole is kind of like where we transition from physics into chemistry. So it's super useful. You're going to use the mole a ton in chemistry if you're going to use chemistry. The mole applies to concentration. Okay, so how much of a substance is in a solution or mixture compared to the other substances, or just in general, how much of it is in there. All right, that's what concentration is. And then you've got molarity. Okay, it's another thing. And then we've got when you're converting something from mass to volume. So when you're trying to look at the relationship between the meters up here and between the kilograms, when you're trying to relate those two things, it's a lot easier if you go through the mole to do that. All right. Then you've got percent mass. Okay, that's another thing that the mole is useful for. Like how much of this rock is carbon versus all the other stuff in that thing. So it's like, moles of carbon because of what the molar mass of carbon is. You know what? Let's do this. We're going to kind of transition into chemistry using physics right here. Okay, so there we go. So in chemistry, you have the periodic table. Let's say we have carbon, right? So carbon has an atomic mass of like 12.01. And again, that 0.01 comes from the other isotopes of carbon. So there's carbon 12, the most common. Then you've got like 13 and 14 because they have an extra neutron. And there's so many less of them that this is the average. Okay. Now, carbon, the atomic number is 6 because it's got 6 protons and 6 electrons. All right. Cool. So the molar mass of carbon, okay, is 12.01. That is the molar mass of carbon. So if I want to know how much carbon there is in 100 grams of carbon, so I have 100 grams of carbon. All right, molar mass means 12.01 grams of carbon are in 1 mole of carbon. Okay. If I have 100 grams of carbon, then how many moles of carbon do I have? You see that? See how you can kind of identify relationships using the mole? You can do this problem on your own if you want to. How you do this is you look at molar mass. So you go from mass to moles, moles to mass. We'll talk about that a lot more in the chemistry video. So that is kind of what physics is. Okay, so that's what physics is. These are the fundamental sort of like units that cause existence and all the things that we experience in our day-to-day lives as not only as organisms, but how atoms and how how molecules interact. Real quick, I'll go ahead and give you a little bit of an example of kind of where these are applied again. So let's talk about physics that's more applicable to kinesiology, for example. So in kinesiology, we have, biomechanics and functional anatomy, and we need to be able to calculate, like lifting, like Olympic weightlifting, like power, for example. Now, before you get there, you have these other units, which I'll write down here in this video, and then in our video about physics separately, we'll kind of break it down a little bit more. Okay, so here are some basic equations right here that you might recognize. So this is the equation for like how you get displacement, how you get velocity, and how you look at the relationships between displacement, velocity, and acceleration, right? And then force is mass times acceleration. So that's how you're kind of analyzing these different relationships there at the top, right? So we'll go through a lot more physics than that in our next video on physics. But just as a there we go. I guess I'll leave that there. Just as an introduction to physics, that's kind of where we're going to go in our first video about that. So that was physics. Now we'll go ahead and head into chemistry next. So when we were talking about physics, we already kind of talked a little bit about chemistry, but at kind of another level, chemistry is basically the study of how all the things on this table, all of these things, okay, how all of that stuff interacts. Okay, so like how bonds are formed, how bonds are broken, and this is where temperature really comes to shine. Like temperature plays a big role in how all these things interact as well. Charge, temperature, all that stuff. So what I have here labeled actually are the most important, in my opinion, kind of atoms or elements to the human body, the human movement system. All right, so the organic molecules that really matter, you can remember this by saying CHNOPS. Okay, those are the most important atoms that you can remember. I've also listed selenium, iron, sodium, calcium, zinc, iodine, magnesium, chloride, or chlorine. Chlorine would be the gas, which is like two chlorides together. So chloride ions, potassium, copper, and then I believe it's manganese as well. So all of these things are super important. There are some more that are required in trace amounts. But the fundamental, most important things to biochemistry, organic chemistry, biology, as we start to zoom out, are going to be these CHNOPS ones, right? So we'll kind of look at chemistry through the lens of the ones that we really want to look at. Let's go ahead and zoom in on carbon. Now, when you're looking at carbon, just like I said earlier, right, you've got an atomic number, okay? Let me get a pen out. You've got an atomic number, that's at the top left here. On most periodic tables, it's laid out kind of like this. Then you have the name of your element, okay, which this is an atom. This is a carbon atom. Then you have the atomic mass unit measured, see 12.01 here. The atomic mass. So this is the average mass of isotopes found in the world of carbon. So carbon-12, as you can see, is the most common isotope of carbon. All right, so that's what that means. And then we've got kind of this conveniently laid out charge here. This shows that carbon really likes to make 4 bonds. All right, and see a boron over here with the 3. You'll see boron likes to make 3 bonds. And then, so on and so forth. You'll see oxygen, -2. It likes to bind to 2 sort of more positively charged things. Okay, so let's take water, for instance. Why does water happen? Well, let's take a look at the kind of... We'll get more into depth into this in an actual chemistry video, but for now we'll just say it's oxygen and hydrogen. Okay, so how the heck does that happen? Well, oxygen has a charge, we'll say it's -2 in this case. Hydrogen has a charge of 1 in this case. So I keep saying in this case, and you'll find out why in the chemistry video. Oxygen's got these electrons on the outside here, and then hydrogen's got 1 electron here. I think we already talked about this, how you have a valence shell, and for oxygen, it's got 1, 2, 3, 4, 5, 6. Hold on. 7 and 8. Yes. Okay. It's got 8 protons and 8 electrons. So 7 and 8, which means that in order to fill its valence shell to be happy, it has 2 empty spots, which means it likes to bind to 2 things. Now, hydrogen, for example, is a great contender because of hydrogen has 1 electron in its valence shell, and in the innermost shell, you can only store 2 electrons. All the rest, typically, you can store 8. Okay, so that's why there's 8 here in oxygen, and then hydrogen's got 1 empty spot, right? So hydrogen's got 1 empty spot. So how are these guys going to interact in order to solve that problem? Well, hydrogen is going to insert itself here to share its electron with oxygen, and another hydrogen, it's got an empty space there as well, is going to insert itself to share with oxygen, okay? So now both are happy because they are simulating having a full octet, that's what that's called, or having a full valence electron shell, so they can be happy. They're at the lowest energy state that they can be in. They're the most stable when they have a full octet. That is why if you go over to the far right end of the periodic table, these are called the noble gases: helium, neon, argon, krypton, xenon, all that stuff, right? These guys over here, they don't really care. They don't really bind with things or make bonds. They're called inert gases, except when you talk about like sonosenescence, which maybe we'll talk about that later. It's a really cool thing. Maybe I'm getting off a little topic here, but that is the reason why like submarine propellers break down. And that has more to do with those kinds of gases and why they kind of light up and everything when you apply electricity to them. But they don't like to make responds. All right. That's the basic information there that you need to know. I think we'll leave it there for chemistry right now, and we'll talk a lot more in the video. We talked a lot about physics today, but there's a lot to talk about when it comes to physics, especially when you're talking about kinesiology and biomechanics. It's all going to have to do with your geometry, your angles, and of course your physics. So there's a lot of mass involved, a lot of displacement. Like, what are you doing? Okay, so that's why we got to talk a lot about physics. And then chemistry comes in when we zoom out again and we get to organic chemistry and biochemistry, when you're getting kind of larger level interactions in your body. So biochemistry comes in once you zoom out some more and you get into like the proteins. So you get like allosteric inhibition and your little machines that are running your body, they're proteins. Okay, so we already started talking a little bit about what biochemistry is and kind of how this kind of feeds off into organic chemistry as well. So we'll kind of loop them together for now because we can, and we can kind of zoom in and out. Biochemistry I see is kind of like organic chemistry working in a biological system. And you'll see why after we talk a little bit more about it in another video, of course. This is kind of an overview. With our biochemistry, we're asking questions about how proteins interact and how metabolism works and how organic chemistry is happening in biological systems. So we've got things like glycolysis, the Krebs cycle, that kind of thing is happening in biochemistry. We're looking at rates, like, for example, this equation right here, substrate, We'll get kind of into what this is. This is Michaelis-Menten kinetics. We'll kind of get into that a little bit in a later video as well. So this kind of relates to this sort of curve right here, if you're familiar. This is about rates, reaction rates in biochemical reactions. And then we've got some funky looking equations, like, for example, Gibbs free energy. And in a biological system, it's referred to as delta G naught instead of just delta G. That's negative RT ln K at equilibrium, or we can call this Q for a system that's in flux. So we'll call this Q, plus. And we'll kind of get into what all this stuff means in a more biochemistry focused video. But this is kind of like those, like the kinetics and kind of like practical application of the organic chemistry. So the organic chemistry is kind of like defining what all of those things are, what the reactions are, and then the biochemistry is like, okay, well, this is the ones that are happening in a biological system, and this is how they happen, and how fast they happen, and why they happen, and all that stuff. So let's go ahead and move on to I guess I'll give you a little bit of organic chemistry. So organic chemistry is like, we've got our functional groups, which we'll talk about. Super important for like the MCAT, for example, if you're going to take that. Just, again, those CHNOPs, those are organic, kind of elements that create organic molecules, which happen to be in carbon-based life forms, right? Like us. So let's go ahead and move on to the next zoom out because I don't want this video to be too long. It's already kind of too long. Now, what is biology? That is a difficult question to answer. And most answers in biology are, it depends. Okay, so when I think biology, I think, okay, the answer is it depends. All right. Now, biology, to kind of break down what this is, let's look at, we're still zooming out. So now we're at like a cell. We were at proteins and systems. Now we're at kind of like the cell. All right. And in the cell, we have cycles. So we've got like, our growth cycles. So like G0, G1. We got our S phase. We'll talk more about this as well. G2. Or we'll go ahead and go into, I don't know why I put that there, into our M phase. Okay, so this is kind of how a cell lives, is it just goes through this cycle right here until it's an S's essentially. Okay, and then you've got your M phase of the cell. And the M phase, we'll talk about that more. That's kind of like cell division, right? So you have mitosis and meiosis. You got meiosis 1, meiosis 2, all that good stuff. We'll go into what that is, your prophase, metaphase, anaphase, telophase, and then cytokinesis for when they split, right? So you've got all that stuff. So this is kind of like basic just cell biology. And then you have, your like organelles, like you have the Golgi and the endoplasmic reticulum, and you've got your nucleus, your nucleolus, like how all that stuff sort of interacts. And then at kind of a higher level, it's using biochemistry and proteins to kind of make things happen. And an example of that would be like Sec1331, which is like a transport protein that kind of like envelops these vesicles that move on down in the Golgi apparatus. So that's kind of where biology stands in this whole mess of science. And then we'll kind of zoom out and we'll get to like organismal level biology. And that's where you're looking at all of the organs working in an organism. And you'll look at the organism. All right. And then after organismal biology, then we get to more like population level biology. So like ecology. Food webs, all that stuff. And then if you just zoom in on the human aspect of that, then we have like sociology and psychology and human behavior. And we get into like sports psychology and motivation theory, intrinsic motivation, all that stuff. Right. So then after our biology, which we'll talk a lot about, that's kind of where we are, right? Where we fall as personal trainers or as athletes or as learners or as people in this video, watching this video. That's kind of where we fall as the biology level, is we are humans, and that's kind of where we are. We're in organismal biology, okay? That's where we exist. We live there on the zoom in and out. Because of behavior is what we kind of are. All right, so then if we zoom out even more, past population, so past like, the study of, how we interact, like be past the sociology, past, even immunology is zooming in a little bit. What am I trying to say? I'm trying to say, like public health, past that. Then we have earth science. So that's where we are, where I need to scroll down here on this little list is earth science. Okay, so what the heck is earth science? Well, let's talk about it a little bit from as far as I know what earth science is. So earth science is like geology, right? Talking about rocks, talking about how things formed, like craters and, even looking at history through the lens of Earth. Like that's earth science. And you've got like climate science. So climate, right? A very real thing that for some reason some people still can't understand, that's just, it's science. Like it's an actual thing. It's not some belief people have. It's a thing that is happening, and why weather exists. Weather exists because of climate. We can talk about that in another video. Okay, that's like chapter 2 of an ecology textbook. Sorry, I got a little passionate there. So we've got climate science. We've got, atmospheric science. That's another kind of version here. We can talk about volcanoes. We can talk about, like river systems. This is kind of where what I was studying falls in as well, like environmental science and environmental chemistry. That kind of stuff. That's earth science. So like your basic, like what you're learning in, I don't know, let's take 9th grade, 8th grade, depending on what state you live in. If you're in a more progressive state, you might have learned that a little earlier. Okay, so that was kind of earth science, at least at a very basic level once again. So this is an overview of like how I see science, like how I zoom in and out to answer certain questions at different zooming in and out levels. So all of these things interact so that to make up the world that we live in. Okay, all of these things, they're always happening congruently. So like when you're in physics class, all of that stuff applies to chemistry, and all of that stuff applies to biochem, and all of that stuff applies to nutrition, and all that stuff applies to like your weightlifting, right? So all of this all combines together, and then we can look at human movement, and then we can look at performance, and then we can look at medicine, right? So you need all of this stuff to working together and an understanding, at least a basic understanding of all of these fundamental pieces of this thing that we call science to then understand how to find solutions to problems. Like, people are working on a cure for cancer or something, and people are working on, they cured sickle cell recently, actually. So you needed to look at all of this stuff. Those researchers needed to know quite a bit of this stuff. Maybe not everything, but all the stuff that they needed to know. Okay, from the chemistry, the biology, from the biochem. They probably looked at genetics. They definitely looked at genetics, I promise, to then sort of go in there and mess around and cure sickle cell. So then after we have all of that stuff, then we kind of get into an even bigger zoom out. So zoom out as much as you possibly can. Then you've got astronomy, theoretical physics, and theology. Okay, so this astronomy is kind of like, okay, this is the planets, this is galaxies, this is where NASA's realm is over here. All right, so we got NASA over here. And then in theoretical physics and theology, this is the two, like, maybe they work congruently, maybe they're battling against each other a little bit. They're always trying to fit in with one another and answer the questions that we can't explain with the knowledge that we currently have. So like Isaac Newton, for instance, like we didn't know about, people knew things fell, but they didn't know what gravity was per se. And he invented calculus so that people could sell wine barrels and make sure they had a more accurate description of how much wine was actually in that barrel because it's curved, right? Calculus is all about just like taking a curved thing and chopping it up a million times and turning it into a box so you can easier calculate the area or volume of that thing. But then you get into theoretical physics, and like quantum mechanics is a very real thing that I don't really understand very well, and I'm not going to pretend I know everything about theoretical physics, theology, or astronomy. I don't. All right, I am a coach, a personal trainer, and my formal education is in kinesiology, biology, and chemistry. All right, and a little bit in what kind of medicine I had to know to take the MCAT, all of that stuff, right? I also published research in social work. You can check out my research if maybe, I don't know, if you've got a PhD and you want to know about that, whatever. But that's a topic for another time. So then we have theoretical physics and theology, and these are the things that answer, or at least seek to answer, the questions that we don't yet understand. Okay? So when we don't know something, we either try to explain it with theory or we throw God at it. That's how I view it. This is how I view science. We've officially zoomed in and out of all of these levels, and after we get through all of this, then it goes back to math again. This goes back to math, and then math goes into pure math, which again I don't know much about. There's like knot theory. Okay, there's imaginary numbers are not that far off. They're actually like really useful. But this is kind of how it works. So let's go back to that again. Let's see what we've made here. We've kind of zoomed out. This is what we've got. We're back again at math again to figure out the answers to the questions that we don't know. And then it goes through that cycle all over again. So when you're thinking about something critically and you're wondering how something works and you don't know the answer, I guarantee you can find it somewhere in here. You just have to know where to start asking that question. Okay, you can always zoom in and out. So that's kind of what the idea with this video was, is to kind of like map out what my understanding as Coach Nate, what my understanding of science is. Like, this is what science is. It's this process. It's the process of using the scientific method, which I'm sure you probably learned about in middle school. It's about using the scientific method to answer questions and then zooming in and out. That's what science is. Thank you guys for watching this video. I know it's super long. If you made it to the end, thank you, thank you, thank you.